Welcome to The Explainer. Today, we are looking at something absolutely phenomenal. Now, for years, we've all been hearing about the incredible things artificial intelligence can do in the virtual world, right? Generating text, playing video games, solving complex math. But taking that AI, pulling it out of the digital realm, and dropping it into the high-speed, chaotic, intensely physical world of a real-life sport, well, that is a massive, massive challenge. Today, we're exploring Sony AI's Project Ace. It's an endeavor to build an autonomous robot capable of playing table tennis against actual human experts. And we're not just talking about gently returning the ball here, but actively, aggressively competing. I am so excited to guide you through the brilliant engineering that actually makes this possible.
Here is our roadmap for the explainer. 1. The high-speed frontier. 2. Project evolution. 3. Sense, tracking spin. 4. Decide, reinforcement learning. 5. Act, mechanical design. And 6. The expert test.
Section 1. The high-speed robotics frontier, bridging virtual and real.
Okay, let's dive into this. You might be wondering, why table tennis? Well, because unpredictable speed is widely considered one of the absolute final frontiers in robotics. If you've ever seen those viral videos of robots moving incredibly fast in a manufacturing plant, there's kind of a catch. Most of the time, those motions are completely predetermined. The robots are locked away, separated from humans, doing the exact same repetitive thing over and over again. But the moment you introduce a human being into the same environment as a robot, everything instantly becomes unpredictable. Project Ace isn't doing some repetitive factory task. It's engaging in a highly dynamic, wildly unpredictable rally with a human opponent who is actively trying to outsmart it in literal fractions of a second.
Section 2. Project Evolution. From bouncing to battling.
So how do you even begin to build a machine that can pull that off? Well, it was a true evolution. The project started totally from scratch in 2020 at Sony AI. Within just 3 months, they had built a minimum viable system, basically a robot that could just bounce a ball up and down on a racket. But that humble foundational system quickly allowed them to iterate. Fast forward a year, and the robot was returning balls and sustaining these really long rallies. Then a brand new hurdle popped up right in their own office. Turns out, one of the team members was actually a competitive table tennis player. Beating him became the new benchmark, and it honestly took a lot of time and effort to overcome that specific challenge. And finally, after about 4 years of continuous, grueling engineering, they reached their ultimate ambition, competing against true human experts.
To reach that expert level, the engineering team had to absolutely perfect what is essentially the holy trinity of autonomous robotics. A complete autonomous robot must do 3 things seamlessly. Step 1. Sense the environment. Step 2, decide on a course of action. And Step 3, act out that decision physically. And here's the kicker. It has to integrate all 3 of these incredibly fast. Let's break these down one by one, starting with how the robot actually senses the world.
Section 3. Sense. The art of tracking spin.
Now, what's really fascinating here is the sheer scale of the perception problem. In table tennis, it's not just about seeing where the ball is. It's about seeing what the ball is doing. Because of Sony's background as a world leader in image sensors, they had a massive advantage. They built this custom sensor fusion array consisting of 16 different cameras, all acting as the high-speed eyes of the robot. They used 9 cameras mounted on towers just to locate the ball accurately in 3D space with absolute minimum latency. Then, 4 cameras are dedicated purely to tracking the human player and their racket. But the most incredible part? They have 3 specialized gaze control systems. These actually zoom in and physically track the ball mid-flight during the rally, specifically to measure its spin.
And why is a dedicated spin tracking system so absolutely crucial? Because of this number. 9,000. That is the RPM, revolutions per minute, of spin that a professional player can exert on a tiny table tennis ball. 9,000 RPM. If the robot cannot perceive that spin, it literally cannot survive a rally. Knowing the exact spin changes exactly how the robot must intersect the ball, its overall strategy, and the specific angle of the racket it needs to use.
Section 4. Decide, reinforcement learning and adaptation. So, the high-speed eyes have sensed the ball and its massive spin. That data immediately feeds into the brain. But that begs a really fundamental question. How on earth do you program a robot for every possible shot? Take a moment to think about that. If a player uses topspin, sure, you could write a rule to close the racket angle. If it's backspin, you write a rule to open it. But what happens when you introduce a human opponent? A human is going to constantly change their behavior during a single game, just to exploit any weakness they see in the robot. Hard-coded rules simply fail against that kind of human unpredictability.
The solution wasn't to just write more rules. The solution was reinforcement learning. This basically means learning through trial and error. The engineers created a virtual simulation where the AI played against itself. Whenever the AI did something good, like successfully bringing the racket to the ball or executing a competitive shot, it received a digital reward. This reward updates its internal model, teaching it to produce more of those good actions. It solved the problem itself in simulation, getting better and better, and then that learned behavior was transferred directly into the real world to drive its high-speed decision-making.
Section 5. ACT. Mechanical design for high-speed movement.
So the crucial point is this. You now have an AI brain that can make brilliant, dynamic decisions in milliseconds. But a smart brain is entirely useless if the physical body can't keep up, right? The mechanical execution had to be flawless. The team actually took inspiration from a Scara robot design, which is known for being belt-driven with long arms capable of very fast swings. They placed 3 rotational axes perfectly in line with each other. Why? Because when those axes rotate simultaneously, their speeds actually compound, giving the arm explosive speed. They also added these specialized wrist joints at the very end of the arm, allowing the robot to snap the racket and generate its own punishing topspin or backspin.
But building an arm that fast creates a massive engineering paradox, which is perfectly captured in this quote from the developers. Reduce the weight as much as possible, but we also try to maintain the rigidity. These two goals are total opposites. To make an arm rigid enough so it doesn't warp or snap when swinging at hyperspeed, you usually have to add heavy, bulky material. But if it's heavy, it slows down. To balance speed with structural rigidity, the engineers had to meticulously computer-optimize the components. They stripped away all unnecessary weight and placed materials strictly in the exact spots where rigidity was required. It's a masterclass in optimization.
Section 6. The Expert Test. Augmenting Human Capability.
All right, we have the sense, decide, and act loop perfected. Now it's time for the ultimate climax. To truly evaluate if they had succeeded, they couldn't compromise on the testing environment. They brought in actual human experts and strictly adhered to professional conditions. They found a space with a 5-meter ceiling height, exactly as prescribed by the International Table Tennis Federation. They brought in licensed referees to officiate, and crucially, the human opponents weren't holding back or secretly collaborating with the robot. They were playing completely adversarial matches, actively hunting for the AI's weaknesses and trying to break its strategy.
And in this crucible of high-level play, the robot did something that completely validated the entire project. During one really intense rally, the human opponent hit a shot. The robot's AI brain immediately predicted the trajectory, decided on its strategy, and began swinging its mechanical arm to intercept. But mid-flight, the ball clipped the net. The trajectory changed completely, instantly. In a fraction of a second, the robot's 16-camera array sensed the new trajectory, the reinforcement learning brain recalculated the strategy on the fly, and the rigid, high-speed arm adjusted its swing to successfully hit the ball anyway, all in milliseconds. It adapted to a mid-flight surprise in real time. No way predetermined rules could ever do that.
It's honestly an astonishing feat of engineering. But it's also really important to understand the underlying philosophy behind why Sony AI is pushing these physical boundaries. It's not about replacing athletes. As the project leaders state, the goal is to work with artists, engineers, and sports people to augment their behavior or their capability rather than replace them. It's about providing a safe, entertaining, and entirely new experience for people to interact with and actually learn from.
And that leaves us with a truly mind-bending thought to close out our explainer today. Project Ace fundamentally proves that AI can step out of the simulator and master one of the most chaotic, high-speed, unpredictable physical environments on Earth. It makes you wonder, if an AI can track a 9,000 RPM ball and instantly adapt to a mid-air net clip, what real-world physical frontier will it conquer next? Thank you so much for joining me on this deep dive. Keep learning, keep questioning, and I'll see you in the next explainer.